Ok, alors on va continuer sur ces questions-là.
Let's move on with these AI issues, and now we're going to move on with two tangible examples of how to use AI and its tools in the farming world. And for our first example, I will ask Francis to come on stage with us.
Donc Francis est responsable du pôle agriculture.
Francis works in 𝗙𝗵𝘃𝗀𝘃. He's responsible for the agricultural hub. And he's going to talk to us how AI is used by 𝗙𝗵𝘃𝗀. These are partners of our Adamar project. Perhaps you could talk about it in your exposé. Hello, everybody. I am responsible for the agricultural hub of 𝗙𝗵𝘃𝗀. I've been there for 6 years. I don't know if you know 𝗙𝗵𝘃𝗀, if that says it means anything to you. It's not a startup. We're part of a group which belongs to Leonardo and Thales, who are specialists in the aerospatial world. Specialists, of course, in observing the planet. And within this team, we have an agricultural section which uses all of the radars and the satellites and all the optical elements available to deliver services. We are a service company. In my presentation, I'm going to talk about a satellite which is in the lower orbit. It's called Le Drone, and you're going to show you how to use the drone and AI. We are able to use all the tools that are available to us in order to detect weeds, but not only weeds. The genesis of all this is in 2016, with a specific demand from two agro-industrialists, 𝗙𝗵𝘃𝗀𝗃 and 𝗙𝗵𝘃𝗃. It's the European leader of popcorn, based in the southwest, following problems that they had because there were alkaloids in natura grains and the seeds in their end products. So they contacted us and they asked us to try and find a solution in order to quantify the presence of datura at harvest, and so they could set that apart and improve their harvest. So since 2016, 2017, 2018, we began to work on these problems, look at the capacity and capabilities of detection of these models, how we can begin to sell the product. We call it 𝗙𝗲𝗃𝗃 in 2019. And since then, we have improved. We're looking at a continuous improvement cycle. We've improved our datura detection cycle, and we've been working on that right up until now. We've re-injected. Give you some of the information. In 2025, we've 1.8 million detections of datura in these parcels already. And since 2021, we've tried to complete this approach with other models in order to look for foreign bodies in 𝗙𝗃𝗃𝗃 is called 𝗙𝗃𝗃 crop. This is for leafy vegetables, but also early detection or post or pre-harvest, depending on demand of the market. So we've developed 16 weed models which exist, able to detect early detection as soon as they're looking at the first leaf, right up to the first bug for datura or for any, the morellus with berries. For seeds, and looking at sunflower, we developed geocali seeds, which can detect the different phenotypes in sunflower crops. Today, we're looking at an industrial process, 60,000 hectares, including all of the different departments. You've got 16,000 missions, objectives with different permissions. We're mixing drones with AI to survey all of this. And what's important is that we have to be able to deliver these maps, this cartography, get the data to the farmers as quickly as possible. And we're at 1.7 days post-drone passage. So you're talking about 1.8 million detections, as I told you, of weeds and foreign bodies. Now that's going to be re-injected into the 2026 model, so the model will be even better performing than the 2025 one. So what happens really? I'm going to keep it simple. You have the acquisition which is done by a drone, and we have the cameras. The height of the flight depends on the object of interest and the size of the object of interest. Acquisitions are done the first day. They're sent to a server the same day. They are treated by AI, and they are revisited by our experts before delivered and under 3 days. And this the different formats, which we'll see shortly. The idea is that detection be geolocalized in each image in order to be put into another tool, a shape file or a 𝗧𝗲, a 16V or a smartphone, and so that you can identify the object of interest within the crop in a very specific and precise manner. It's the smartphone factor which is limiting today. With the 3 services then that you see, that's the one that limits most. Now, we've been able to industrialize this because we use high definition with quite a big drone. It's 1.10 meters in diameter, and it's really quite climate resistant. It's got DJI, more or less, and it's able to carry a real camera. So when you have these, when you have your Sony Alphas 7R4 or your Sony ILX, they are 61 million pixels in each camera, which allows you to have excellent definition of what's happening on the ground, depending on the height in which, obviously, the drone flies over the land. At the moment, we're still a wee bit off, but we want to get closer and closer, above 2 millimeters anyway. Now, this is the kind of detection we can show. You're at 25 meters in height when the drone flies over, and this is the kind of detail that you can get with these cameras. And this is 𝗙𝗲 early detection. You can see from the images how specific it is. We're also able to discriminate some plants in a forest, for example, 𝗙𝗲𝗋𝗋, that's a classic example. People say in Spain that there's no 𝗙𝗲 in the parcel, but I'm sure there is. So we go to the parcel of land, we send the drone in, and the farmer's always absolutely shocked to find 𝗙𝗲 in his crop. But this is the kind of detection we have now at our disposal. With others, of course, we can select a particular characteristic of the plant. We don't need to see the whole plant, but we need to see part of it in order to detect it. Now, on the right, you see the level of confidence in this model. And so you can see we have the figures from 2016. We'd like them all to respond to in the same manner when we're talking about this level of detail. And this allows us to see all the plants. As you can see, this in buckwheat. It's one of the most complicated crops to find, in which to find 𝗙𝗲, but you can see even through a tree, you can see it. I like this one. You have to understand that in a given model, you're going to be able to identify, you're going to have some good results, some good detection. You're going to see the plant as, quite well developed, but you're also going to have quite a few false positives. And this balance is important when you give the results to any farmer. You have to go and make sure that you look at all the 𝗙𝗲 and work it, respecting thresholds and the leaves. You're at 0.13. That's the strength of the way we work. Each detection has a threshold, and this threshold is reviewed by a qualified operator who has the appropriate training, who then allows them to deliver the deliverables, saying, OK, look at this, you've got a part of a leaf which looks like 𝗙𝗲. It could be a hybrid canopy cover, but it looks like 𝗙𝗲. There is a doubt. So your threshold is at 0.13. So everything is verified before it's handed over to the farmer. There is no perfect model, let's face it. This is a compromise between, good detection and things you forget. So you're going to have some kind of middle ground. And we can work on several different weeds. So here you've got 𝗙𝗏𝗃. You've got quite a well-developed one and quite a small one. And then you also have nightshade. And since then, we've been working, and this is an example I love, we've developed it in 6 months. You've got potatoes that are regrowing, and we want to make sure we're going to avoid a certain amount of elements in the leaves. So you want to limit the presence of beetles in your potato crop. But so this potato plant with this characteristic doesn't have any equivalent in the parcels, this kind of beetle plant. So you've got 20,000 labels, but there's a certain limited amount of here we're looking at an environment of we're looking at 900 meters around the production area to avoid contamination. And what we want to, when we're doing this, we want to avoid contamination, cross-contamination, pollution. And when you work with seed manufacturers, you have to go and particularly look here, we're looking at sunflowers. What we're going to look for is a particular differentiating phenotype, which is going to indicate the level of maturity of the leaves, is there any discoloration? And this is going to allow us to really streamline their task and allow you then to go and get to identify all potential problems in the environment. And the last that we developed with 2 industrialists, and we're working on it since 2021, it's not weeds. Here we're looking at 3 different types of information that we're going to give them. We're going to detect what? We're going to look at objects, artificial objects. You can see there's a tube, you've got plastic packaging. You can go and find bottles, everything that's plant-based, like, for example, bits of corn stalk. And here's a large stone as well. And the same image, we can get lots of different information. So we're actually combining lots of services into one. So that's a little bit of information on what we're doing today. Now, the goal, of course, is to continue. What we want to do to make sure that this information can be used and be used by the farmers and agro-industrialists. So we need to be able to integrate it into, for example, smartphones to have a manual purification streamlining, because we're able to look, that we're able to identify a certain percentage of cover, so you can detect where the weeds are on the parcel. If you look at thistles, you can see there was an 80% reduction last year through this technology. We can have harvest projects where we have parcels which are untouched, and then ending up with parcels where we have datura, etc. So it's interesting to have this map, which allows us to detail the progression before we start harvesting. When it comes to the agricultural material, whether it's hoeing or grinding, there's a message for all the robots here, for the robot producers. If there could be any kind of interoperability, it would be good. That being said, what happens? Well, the method is fairly simple, but I keep having to repeat it. You have the acquisition, you saw the pictures, and then given the images you're going to see, you are going to begin, and this is the most fastidious part of the job, to go and label the images with where there is any kind of object of interest, for example, weeds. This is a very important point, even though it's tedious. You selection then different types of neural networks. I gave you a few examples. We're not working on one specific one. We like to mix them. It's a combination, and then we customize the networks in order to go and look for the maximum number of detection points. You have networks that will give you more false positives, others which don't. So we mix them, we constantly set challenges, and we assess the networks and before we unroll them. The next important phase is control. We call it quality control. And here all of the images that have been processed, once we've delivered the service, all the images are reviewed, qualified, and reintegrated in order to keep the images from the start of year, from the beginning year, and also to include the images from the year underway. In 2022, the datura model had never actually seen any datura. 22 was very dry. It was a dry year. The datura plants dried in the field. So what happened was we were out in the country. We were trying to detect datura that the model had actually never seen, because there were no more leaves, there were no flowers, there were just the stalks. And for industrialists, well, stalks with their juice are a source of contamination, so we had to detect them. Now, we realized that over the course of the season, so we looked for images with this type of datura, which was completely dry, and under 3 days, we were able to redeliver the images and go and get the detail. Of course, it wasn't a non-exhaustive list. You need context, you need a great many images. In 2023, once we had that context, the model worked perfectly. That's it. We're always undergoing continuous improvement, looking at the context, which can change year in, year out. So we have to always move and roll with the times and improve the model. So this is what we took information over the course of the season, and we can inject that into the information base for the following year. I hope it's clear for you all. In the 𝗙𝗏 project, we had enormous challenge to try and detect ragwort. We use the same material. Looking at the height for detection, it depends on the type of fusing we were using. What were we looking for? These were the parameters to get a shot. You had the beginning of the project was very short because we fly at 2 meters per second. With the others, it was 4 and 5 seconds. So we had to look at the speed and why we changed it, but it was principally for the quality of the image. Now, here, you're looking about 10 different kinds of weeds, of crops, excuse me. You've got sorrel, artichoke, thyme, and all the rest of them. And there, I'd like to ask you all, if you have ragwort at the beginning of next spring, we are takers. We'd like to come and take pictures and help. It's very important for the future of the project. And we've begun to label here with full crops, with sorrel, artichoke, echinacea, lemon balm, and we've just started with coriander. We're going to label them. We have a 4-flower stage right up to the blooming stage. So here, I don't know if you can see it. This says ragwort. We are going to go look. We're going to labelize this type of detection. We're going to label it, not labelize, excuse me. A label means one detection. You have images which are 200 square meters. What you then have to do with our experts to pick up on each image and to go and search for these images with a fine-tooth comb in order to label them and to begin to really identify them for what they are. This initial model, and you can see the photo here, well, we cheated a little bit here. We're going to go to parcels which are not cultivated. They're not necessarily target parcels, but it allows us to have a context where we can train ourselves to spot these weeds. So there are about 6,000 labels currently now for the different crops, and the first model has come out. This model has allowed us to speed up in terms of labeling. It's going to detect real and false positive ragwort detections. We're going to be able to speed up the process now. We're going to speed up the process of identifying ragwort in different parcels and for different crops. I hope that's clear for everyone. The first model is created, as I said. We've got 1,500 labels for this first level, and I think we'll have more than 6,000 before the end of the year. So that will bring about the delivery of a second model, probably come into fruition around about May or June. And by way of a conclusion, these are your takeaways. Look at the object of interest, or the weed. It can be more or less easy to identify, or more or less long to identify it. Depends on the characters of what you can find in nature. I'm not worried about ragwort because the diversity of shape is nothing compared to datura, which can be very difficult. Datura can bloom at 10 centimeters above ground, but it can also bloom at 3.5 meters above the corn. It has different shapes and forms which are quite incomparable. So even just through its size, we have to be careful to have quality in our database. We're lucky to have this expertise in Malherbe. If we look at the contribution, if we call on the public now and again, we are including various, random elements, because not everybody has the same level of knowledge with this point. AI is never fixed. All of the models are being improved consistently. Every year we're going to re-inject more images in, and that in turn creates the diversity of the group and the context. And when you talk about diversity of context, is when you have the acquisition of images, the type of soil, the geographical zone, light, luminosity. We're very busy in Spain at the moment. We're flying over fields now, parcels for Natura and Nightshade, but we've also begun working in Great Britain, and of course the context is very different. But the model is going to learn continuously from the various contexts around Europe. And finally, one model is never perfect. Keep that in mind. It's always a compromise between real positives and false negatives, apparently. And we have to have this trust threshold, which has to be as comprehensive as possible when you deliver your models. And what's perhaps worrying for the ragwort model is economic feasibility, because the lower we fly, the more we're going to see the beginning of projects which are very feeble. So unfortunately, the costs behind that are very high. I'm going to have new sensors that are going to arrive on the market. Pixels are going to change. We've got one that's got 150 million pixels, which is going to give us far more precision and allow us to fly higher and to have a better shot at the beginning of a project. You're also going to have the capability to change the cost with the hydrogen batteries, which allow us to fly higher. Battery shelf life is about 45 minutes there. Now we're going to go up to 2 hours. We're able to fly for 2 hours, maybe 2.5 hours when we're flying over. So that's going to help us in terms of cost and efficacy. We are carrying out tests in almost like swarms of drones flying together. And if you see what we're doing we look at autonomous drones, we've been really increasing the time of flight and lowering the costs at the same time. So there is still a legislative issue to be addressed, although it is well entailed and well monitored. But when we look at autonomous drones, today you have to bear in mind that they can be completely autonomous. Do I still have a minute? Well, just a short one. We have a service, it's called a department, 𝗙𝗍𝗶𝘀 in Canada. So what we're doing is we're flying over recreational and therapeutic cannabis. We have a drone in Toulouse who is going to recharge in electricity in Toulouse and going to give us the information. So you can imagine that this drone is being used in Canada. So it would allow us to detect weeds in the morning, and in the afternoon it can go and look at something else. The drone can be used for other purposes. Tomorrow, the technology is ready. Tomorrow, with the legislation, we're going to make sure that these autonomous drones can work independently, and we'll be able to transfer the information directly to our server for processing and delivery. So the perspectives are pretty good, really good actually. What you must bear in mind is that we're really at the beginning of the creation of AI in this field, in the agricultural world, I should say, with perspectives in which you must believe, and there are possibilities out there. But this is not going to work if we don't have the expertise and the agronomic intelligence that's necessary. We have the databases, but some of them are of quite poor quality, so all that needs to be improved. Thank you very much, Francis. Thank you for this very clear presentation, which shows us the application of AI and shows us what we can do in projects where different stakeholders are involved, as we saw with 𝗙𝗨𝗪. We're a little late, so I will allow one question. Just one. Nicolas? Short question, please. In the maps, we've got 36,000 crops. So you detect weeds, that's great. And if you could destroy them, it'd be even better. There are companies now which are beginning to do that with AI, aiming at mechanic destruction, either with lasers or with spraying. It's a costly endeavor. You have to carry out algorithms for specific crops. So I wanted to know that if you discuss with these people, do you sell your algorithms to other countries so that we could have products which might finish by being within our price range? No. Not currently. We do talk to some companies, but it's more in terms of complementarity. We don't want to offset our system against theirs or one system against another. I don't know if I can cite them, but I'm going to. 𝗙𝗏robotics, we work indirectly with them, but through agricultural distribution, because we use our technology in order to direct them towards the tool to use. We can fly over some arable crop parcels, for example, with green beans. We're going to see that there's a leafy surface which has to be destroyed, and depending on the foliar surface, if it's 80%, there's no point sending an 𝗙𝗏robotic. If it's 20%, that's worth it. 80%, we would rather just spray, targeted spraying, for reasons of cost and economy, and then we would use 𝗙𝗏robotics for the rest. So we would tell him the size of the surface that needs to be treated, and he's going to have to do it. So we're used more as a decision-making tool here, observation, rather than somebody that takes a final decision. And when it comes to the sharing of data, we're not working on the same systems. We discuss the methodology, but since we're not working with the same images in terms of acquisition, our models don't work in a similar fashion. So we would have to work hand in hand and have the same sensors in order to have something that would be remotely beneficial. But we are complementary. Same for targeted spraying.